Okay, so welcome to the Unit 10 podcast on section 17.2. Today we're going to be discussing the factors that affect rates of reaction. One of the factors that influences how fast or slow a reaction goes is the nature of the reactants themselves. They do influence the rate of the reaction, and based upon some of the things that we've talked about earlier in the year, we know that some substances react more readily than others, and this of course has an effect on the speed of the reaction. For instance, if we compare calcium to sodium, just by virtue of the nature of calcium versus sodium, there's a difference in the way they'll react. So for instance, if they both react with water, the reaction with calcium with water is relatively slow, and this is illustrated here by this blue test tube, the blue background for the test tube. For sodium, it's a much more rapid, violent reaction that is illustrated by the test tube in the black background. And the reason why there's a difference in reaction is simply because of sodium versus calcium. If you remember, calcium is a group 2A metal, which means it has two more electrons than the nearest noble gas. So calcium, as it forms calcium hydroxide, gives its electrons to hydrogen. Whereas sodium is in group 1A, and 1A metals, one of the reasons why they're more reactive is because they have that single valence electron. So they're just one extra electron compared to a noble gas. So in its desire to stabilize and to be more like a noble gas, it'll actually rapidly give up that single electron away and become sodium hydroxide. So part of it is due to the substances themselves. Concentration is also a factor. So concentration just basically means the amount of reactants that we have. In general, when we increase the concentration of reactants, that also increases the rate of the reaction. The rationale behind this is related to our collision theory, which we talked about in the last section. More particles in solution means that we have a greater frequency of collisions. More collisions that occur, the more likely those collisions will result in the formation of products. So you can see in low concentration there are few collisions, whereas in higher concentrations more collisions are possible, and according to the theory you should get a faster rate of reaction as a result. Another factor that influences the rate of the reaction is known as surface area. Surface area is basically the amount of reactant exposed based upon the form it is in. The idea is that the more surface area that is exposed, the more collisions that you would see. So let's, for instance, say we have a large chip versus a bunch of smaller chips. You can see here if these red particles want to react with the large marble chip, there's only a certain amount of area exposed. So you can see here only things that are going to, since this is two-dimensional, only things that could combine with each side of the surface could possibly combine and react. Whereas here, in smaller particles, you can see that there's greater total surface area exposed if we compare the small chips versus the larger one. And as a result of this, the rate of the reaction would increase. Temperature is also another factor, and this is something we talked about in our glow stick demo lecture from previous. The idea here is that for most reactions, if we increase the temperature, it also increases the rate of reaction. Now temperature actually has two effects according to the collision theory. So there's an increase in kinetic energy obviously as the temperature increases. What that results in is a greater collision frequency, so you're going to have more particles colliding, but in addition to that they'll also collide with greater force than they would at lower temperatures. In this figure here on the right here, you can see T2 has a higher temperature. Notice the greater, if the shaded area represents the percent of particles reacting, you can see that there's a greater area for the higher temperature than there is for the lower temperature in comparison. Catalysts, and this is something we introduced in our discovery lab, are substances that increase the rate of the reaction without itself being consumed. Enzymes are probably the most familiar catalyst for you guys. You talked about them when you did metabolism. So think of your Krebs cycle, cell transport, glycolysis. So enzymes are biological catalysts, and most of them are protein based. However, there are other catalysts that lower the activation energy. All catalysts lower the activation energy, but there are other catalysts besides enzymes. And just like there are catalysts that, allow reactions to go more quickly, we also have the counter to that, which are inhibitors, and inhibitors slow down or stop a reaction rate. We can see here that the way catalysts function is by lowering the activation energy. So this first energy diagram with a darkened line represents the activation energy without a catalyst. So notice how much higher the activation energy is here versus when you do have a catalyst. So that's similar to what we saw yesterday or the other day when we did when we added the yeast to the hydrogen peroxide. Now to kind of continue with catalysts, there are different kinds of catalysts. One kind of catalyst is a heterogeneous catalyst. Catalysts that are heterogeneous basically are in a different physical state than the reactants are. There are many different heterogeneous catalysts. A lot of them are metals related to chemistry. For instance, palladium, platinum. Catalytic converters in cars are actually heterogeneous catalysts as well that catalyze the breakdown of things in your car. This is what we call an adsorptive process. This is not a typo. What ends up happening during adsorption or in heterogeneous catalysis is the thing in blue is the catalyst. So I'll number these. And what happens here is the reaction is actually happening on the surface of the catalyst. So this is what adsorption means, and this is how a heterogeneous catalyst functions. Homogeneous catalysts are probably the ones we're most familiar with. These are catalysts that exist in the same physical state as the reaction it catalyzes. For instance, our familiar enzymes, which are aqueous, react with reactive particles that are also in the aqueous phase. So this is what makes them homogeneous. This is an absorptive process, so they go inside of the enzyme. Okay, this is peroxidase. So this is the enzyme that the yeast had that broke down our hydrogen peroxide in our discovery lab from the other day.